So I will just state two results. We will not have the time to go over their proofs. So I will just skip the proofs. So let's say I have three independent simple symmetric random walks. Let's say one is starting from 2i, another is starting from 0, another is starting from minus 2j. Let me denote this by s into I. Let me denote this by this. Yeah, Z. So we have these three simple symmetric independent random walks. So this like this looks like this looks like this. So let me define their collision time at as the time when this is the first time when any two of the three random walks meet. So this will be yeah on the Z 0. Yeah. So note here that the difference between their starting position is always an even number, and the increment random variables just they take either +1 or -1, right? So the random walks can never cross each other; they can only collide each other, right? So yeah, if I define my collision time to be like this, then what was already known that you would get a result something like this. The expected value of the collision time was known. So our result shows that if you have a constant alpha which is between 0 and 1, then you can get an upper bound like this. Alpha is a constant between 0 and 1. And this constant, the value of this constant depends upon the value of alpha. Okay, so we are just showing that in a neighborhood of 3 by 2, the uh, moment of this tau, it is not only finite, but we can also bound it in this way. So this is our first result. And the another result also, so this was the case when the random walks cannot cross each other, right? So now what about when the random walks can actually cross each other? So let's say we have again three independent random walks, and we are not putting any restriction on the starting position of the random walks, in the sense that earlier we restricted to the cases when all the starting position were even numbers. So if that is not the case, then what we can show, okay, so another in the case of crossing, so this was case of non-crossing and this is case of crossing. So maybe I can write. This is the case of crossing. So in this case of crossing, we also assume another thing. So here the incremental random variables were just IID Rademacher. So they could either take +1 or -1. So all in this case, the random walks were simple symmetric random walk. So the increment random variables were Rademacher random variable. But here we assume that the increment random variables they take value on this set. -m to m, where m is some positive integer. So under this setup, if I define a set like this, yeah, so if you have a set S1 like this, So then our result states that so here I and j are some constant that depend on the initial position of the random walks, and this m naught. So essentially, I am defining a Markov chain here like this. So they denote the position of the random walks as time passes by. Okay, so mn1 is position of one random walk, mn2 is another, mn3 is another. So if that is the case, then our result says that we can give an upper bound on expectation of tau like this. This quantity is essentially depending upon the initial condition of the random walks. This one is this set. Yeah. Yeah. No. Yeah. The increment random. Yeah. 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 So the variance of I is the variance of this increment random variable. Okay. The increment random variable, the variance of that. No, no, we are not assuming uniform anything. It is very general. Yeah. We have one condition that it will take some time to describe all this. So I'm skipping that. Under some regular condition on this distribution, we can show this. No, we are not assuming anything. We have one restriction. I am anyway presenting this in post session, so maybe I will describe it. Okay, so these was my two results.